Okay, so welcome to this lecture that will cover two topics from visualization. So we'll start in 2D and some 3D with the library Matplotlib. So we have been doing some exercises with NumPy for doing array computing. And usually you also would like to do plots connected to your data. And one of the most common libraries that are available through your Anaconda installation and other numerical Python distribution is the Matplotlib library or module. And Matplotlib is a really large library, which is a general purpose drawing library for drawing geometries and drawing colors and stuff like that. But to be easy to use, they also provide a submodule called PyPlot. And PyPlot works very similar to the plotting functions that are available in MATLAB. So you'll probably recognize some of the syntax if you have used the plotting functions in MATLAB. So to use Matplotlib, you have to import this statement here. You can for now ignore this matplotlib inline. This is only when you're running it in a notebook to get plots in line with your text. But if you're running it standalone, you do import matplotlib pyplot as PLT. That is the standard convention for importing pyplot. So pyplot is a simplified interface to Matplotlib, and Matplotlib is a larger library that can do much more than just what pyplot can do. So let's see, just import it here. So it's very simple to plot in Matplotlib. So the simplest command you can do is the plot command, and you just give it a list of numbers, and it will do a simple plot for you. And if you're running in standalone, there is a method called plt.show that would actually open the window and display the plot. Usually you do that if you have multiple plots, you do all the plot commands and then you do plot.show and it will come up as a window. Running it in Notebook, it will automatically plot in line. You don't have to do the show. So as I see for here, this is just a normal list. Everything that you can access by index can be plotted. So it can be any data structure that has the bracket notation. So the plot command knows how to iterate through the list. But of course, we want to plot NumPy arrays, so we import the NumPy library. And in MATLAB, you can define a range using 0, colon, and then a step, and then an end. It would be tempting to use the A range here, as I showed before. The problem is that you don't know that it includes all the values that you want. So there is a better command called linspace that tells you the starting point of the range you want to plot and the end value. And linspace will guarantee you that you have both the starting value and the end value in your X range. And then you just tell it how many values do you want. And then using the array notation in NumPy, you can create a Y array, which each element has this sign value here in this case. So it's very similar to what you do in MATLAB when you want to plot. You first define the X range, and then you create the Y range using calling the sin function here. And if you run this here, you can see here that I get 0 to 50 values here, from 0 to 2 pi. And then here is the sign calculated on those values here. If I do, for example, only 10 values here, you see I get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the last one is how many values you want to range. But you are guaranteed to get 2 pi at the end value here. So now when I have an X range and also an array, and I also have a Y array, you can plot X against Y using X comma Y here. Oh, this is a bit ugly, so I will change this to again. So now it's much nicer. So by default, it will automatically scale the labels, the ranges, and to fit the curves. You can also change the line type of the plots using the third parameter here. In this case here, red means R means red, O means I want circles. So then I get red circles like this. You can do blue circles, and I want a line as well. Then I get blue circles and a line between them. And if I want a dashed line, I can do blue and then two dashes like this. Then it will do a dashed curve like that. And if I do B plus, it will do blue plus signs. And then if I have plus and dash, it will do pluses and a solid line like this. So it's very easy to quickly do plots, and you can combine them differently as well. So one nice thing is that you can actually do quite complex functions here. So in this case here, I have this f of x sine x plus sine 3x divided by 3, and so on. And here I can first I create the range I want to plot using the linspace here. I have 200 points here. Then I create my function here using the array notation NumPy. So this will calculate sin on all the values of x. Same thing here, this will calculate sin 3x divided by 3. So that will operate all the elements in the array. Then I plot it here with a blue line. You can also do multiple series in a plot. So in this case here, I have a single x range that I want to plot, but I have two y functions I want to plot. In this case, sin x and cos x. And I need to have them in separate arrays because otherwise I can't plot them separately. Then you can actually do first here that this is the first plot, and this is the second line here. So you just continue adding x, y, and the plotting parameters. You can continue doing that multiple times using this function here. So now I can combine them both in a single diagram. There's also you can also add name parameters at the end. So when you're done listing your series, you can add extra parameters here that are named. For example, if you want to change the line width or the lines, I can specify the line width option here. So I want a 4-pixel line here. So now you can see that they're a bit bigger, and those will apply for all the series. So if I put a single parameter here, it will go for every series I plot. Then, as you know, Python is object-oriented. So the plot command actually can return the separate line series for us. So in this case here, I have two lines here. So the first x, y here we go. This is the line series for that plot, and line 2 is the second one. And I can set properties on these lines separately. So in this case, I can set line 1, set line width. And so one is 4, and the second one is 8. And then I plot show here. So now you can see the blue line is thicker than the red one. So in this way, you can actually get out this individual series and modify them separately. You can also return a list of lines. In this case here, so lines equals to plot. And then you can do set properties on all of the line series in the lines list here using the set p method of the Matplotlib library. So this is more for when you're running it in a separate standalone outside a notebook. Then you can create multiple windows, and you do that by calling the figure 1 here. That will create a new figure window. and the next plot command will go to that figure window. If you go, then you create another one, figure 2 here. Now the current plot is figure 2, and if you do plot, it will plot in the second window. Running it in a notebook is a bit odd here because you get 2 images on top of each other. So this is the first figure and the second figure. Running it as standalone, you will get separate windows that you can move on the screen also. So it behaves a bit differently when you're running it in a notebook or out of a notebook. In some cases, you would like to combine multiple plots in a single plot. You do that with the subplot command. And subplot defines the current subplot you want to use. And the format is the first numbers, they give you the number of rows and columns of the plot. It's a bit odd way of doing it. So in this case here, 2, 1 means I have 2 rows and 1 column. And then this is the first plot. And then you have to repeat 2, 1, and then the second plot. So here I have subplot 2 rows, 1 columns in the first plot. Then I put, that is a second plot here, and that will give me like this. So this actually is a single plot. It's not 2 separate plots, it's 2 plots in a single image. And then I can do, for example, 1 row, 2 columns. And then it's a bit different. Then you get this instead. So you have 2 plots next to each other instead, 1 and 2. Sometimes you also want to add axis labels, and here you can use. So in this case, I create figure 1 here, subplot 2, 1 like before. I label the x axis x and the y axis y1 using the x label y label command and plot it. And do the same thing with the second subplot. So now you can see you have y2, y1, y2, and then x here as labels. A really cool feature with Matplotlib is that you can actually add text to the plot using LaTeX syntax. So if you have a formula here, in this case here, I have a text here with a math formula. So you need to use the $sign the beginning and end to indicate that it's math mode. And then you have your formula here. You specify in plot coordinates where you want the text to go. So this is the actual coordinates in the plot, x and y. And also here, how you want the text to appear, right, center, left. Okay, I need to. So you can see here that I have a formula here, which I added to this point here. So centered around this point. And it will interpret automatically the output as a LaTeX formula. So that is nice to know that you can actually add formulas inside your diagram as well. You can also annotate, which means that you can create an arrow inside a plot using the annotate command. And then you start where you want to point. This is the first option here. And then where you want the text to be placed. And then you can set some properties on arrows here as well, with, which color it should be, how large it should be, and so on. And if I run this, you can see here that the arrow points to the position in the diagram here, and this is where you place the text in your diagram. Okay. You can also define what you want to plot using the xlim and ylim functions. So here I want to plot from 0 to pi and from 0 to 1 in y direction. Running this, it's kind of like zooming into the plot like this. You can also change the scales of the axis to be linear or logarithmic using x scale and y scale here. So do an exponential function here, and I plot it with a log scale, and you get a straight line like this. I will just quickly go through, most of this is quite easy to use, so I will leave that yourself to experiment here, but I will go through some of the plots here. So here you can do histograms, like this. You can do bar charts using the bar command. You can do scatter plots. This. Contour plots. Here you have to, if you want to do contour plots or 3D plots, you need to create something called a computational grid. So you do define your X ranges here, Y range, and then you create X and Y. So here you define how many grid points you want. And here you create a mesh grid object here, or X and Y here, which you then can use to create a C value here using a function 0.5 X times Y. Then you get a field X here. We can plot them and see how it contains. So if I do you can see that you have X value ranges here, and you have computed C values here as well. And then you can plot them either using the contour F, that is field contour, and here you specify the color map to use. And if you just want the contour lines, you can do contour, and also same color scale here. So this is how we get nice contour plots. You can also display images. So I just download my classical image here. I can do plot imread, that reads the image from a file. Then I can do plot imshow here to actually show the image. And then it will be plotted just like a normal plot in Matplotlib. And you can see axis on here, you see the Y pixels and the X pixels here. You can also interpolate the pixels when you load images. So it will smooth out images that are low pixel density. We're using different algorithms, filter algorithms. You can do streamline plots. You also have this grid here. And then you use the stream plot here, different combinations here. So you can do stuff like this. Bar charts. And you can also do 3D plotting. So this is the first part of visualization. So I will refer, Matplotlib is an excellent library. So if you go up here, there is a tutorial section here with a lot of information. And a very nice thing as well is that you can go to the gallery section here. And if you're looking for a plot, you can just browse through here and, okay, this looks like what I want, or this looks like I want, and then you can just click on it. And then there's also the source code here for how to implement this plot. So that's an incredible resource to have. in this examples here. So it's a huge library. You can do a lot of stuff with it, and all of these have source code that you can download and modify. So that was Matplotlib. So that is the simple way of doing plots in Python. Next, we're going to look at the tool that is actually a standalone application called ParaView. And ParaView is a general purpose visualization tool that you can use to visualize any kind of data in different formats. I will give a brief introduction to the Para application. Then we will use a library called PyVTK, which you can use in Python to generate data that can be read in ParaView. Let's change. So ParaView is an application developed at the Sandia National Laboratories, and it's an open source application for scientific visualization. And I will go through a bit about introduction, basic usage, and some just mention of how you can bash script it as well. So it's short from this. This is their own PowerPoint slides that they use from the demo list application. So what is that? So it's an open source scalable multi-platform visualization application. It actually supports parallel computation as well, so you can run this on a cluster to do the visualization. Because many times the actual algorithm for creating the visualization is the thing that is computational heavy. Displaying the triangles later is actually less computation intensive than actually doing the creating visualization. So in that case, in ParaView, you can actually divide up the model and you can do the visualization over several servers at the same time. It has a very open, flexible user interface. Can be very daunting when you start using it, but when you get the hang of the workflow, it's actually very logical. It's extensible, has a modular architecture, which we'll see later. It supports a lot of plugins for different visualizations, for file formats. You can get support as well, but it's an open source program which you can download and compile yourself if you want. So, what is scientific visualization? Here are some examples that has been done using ParaView. And you can see here it can handle really large models and visualization of these models. So it is used by universities, governments, commercial institutions. And you see it has a lot of awards for excellent application. And here you can see here some impressive, not just of these old numbers, but 6.33 billion unstructured cells. And I think the number is even higher today. Today, it also can support visualization using directly when you're running computations on compute clusters. You can actually do the visualization directly on the node and produce data during the simulation. So the architecture of ParaView. So what we are going to use in this course is this top level application. So it's called ParaView client. But ParaView actually consists of several applications. You have ParaView client, but you also have something called PV-Python, which is a Python interpreter with all the algorithms that you need for visualization built in, so you can script ParaView, create your own workflows. Then there are some other here, web-based ParaView, and some other specialized. ParaView client and all these applications are built on top of a UI library called Qt widgets, built on top of something called ParaView server. That is the tool you can do for running in parallel. And below here you can see something called VTK, which stands for Visualization Toolkit, which is a large C++ library for visualization. So ParaView is implemented using this library. And that library uses OpenGL, MPI, and many other technologies here to implement the visualization. So OpenGL is a hardware interface for hardware accelerated graphics, and MPI is for parallel computing. So it's a quite advanced application, but you can, if you want to use it on your computer, you can download only the client and use it on your laptop or on your workstation. If you want to do more visualization, you can use Lunac resources, and we have dedicated resources for running ParaView with more than NVIDIA cards. Yeah, there's some version information here. It's quite an old program, so it has over 20 years of history. And we are currently using 5.10. And it's also using some of the modern features of OpenGL standards for high performance graphics as well. So what is the kind of meaning of scientific visualization? Is coming from a lot of numbers generated from your visualization, or from your computational tools. And then you want to interpret this in some way that it's understandable, so you can see the flows around the space shuttle here, in this case, the contour lines of the section of this, to basically understand simulation results. And ParaView has built-in primitives for different kinds of data. So you have the uniform rectilinear data. So that is basically a grid, a structured grid by rows, columns, and sections in the depth as well. You can also have non-uniform rectilinear, so that when you have a vary and this distance of different grid points, you can have curvilinear data, structured grids that are curved. Then you can have polygonal data, which is kind of unstructured mesh with the polygons, and then you have completely unstructured grid, which can contain any kind of element type. And we are basically going to go through some of these here, except for the curvilinear one. So I will put some links on the Canvas site as well, where you can download it and where you can find a user's guide. And there are also several tutorials here to use. So I will actually, instead of going through all the slides, I would try to demo ParaView live, which is always a danger, but I will try. So I have installed ParaView on my Windows machine here, 5.10.1. So when you start ParaView, you will get this message here. If you want to see what you can do, you can press the example visualizations, then you'll get the starting guide. Otherwise, you just close this window here. This. And the basic layout of ParaView is that you have on the left side here, you have something called a pipeline browser. Here you will start by adding your data that you want to visualize, and then you add filters and plugins on top of that to slice, dice, create streamlines, and you create basically a flow of data through your visualization. The blue window here is the actual output of visualization. And then here you have the properties section here, which contains properties of the selected item here in the built-in in the pipeline. Then I have some other function we'll display when I run this here. So I just create some data to visualize. So you have sources that is objects that are built into ParaView that you can use to annotate your plots, or you can create data without having scientific data below. So in this case, you can see here that there's a lot of things you can create, and I will create a sphere. And now I also see something that is a bit odd in ParaView, is that nothing happens directly. So you can see here that I added a sphere object to my pipeline browser, but I don't see anything in the blue section here. And the reason for that is that many times when you use ParaView, the data are so large that you don't want to draw it directly. You want to set the properties before you actually draw it. So in this case here, if I just press apply here, every time you change something, there will be a green button here, press apply. And if I press apply here, you get the sphere object, the representation of the sphere object. I can rotate it around like this. And then you can see also here in the properties section that I have radius here, so I can do 1. Then you see every time I change anything, the apply button goes up, and I can change it here again. And perhaps I want to do it more detailed. I will do 16 steps here and 16 in that direction. Now you can see it's much rounder. And now you see I have it's visualized using something called surface mode. And you can see here the representation here is at surface. There are many different kinds of visualization you can do. So points here will display all the points that makes up this object. You can do surface as we've seen before, that is a shaded surface, smooth surface. You can do surface with edges to display the actual geometry that makes up this object here. So now you can see all the individual triangles that actually makes up this sphere. There is also a wireframe that shows only the lines of the triangles here. So we will continue with the surface here. And you can see here also you can set the color of your sphere. So currently it says that the coloring is done by solid color. If you have data attached to your model, you can also switch to color the data, color the sphere by the data that is stored in the vertices. But this sphere doesn't have any more data. So I can change here. I can create red here. And you see I have a red sphere. To make it more plastic-like, I can change the specular highlighting here so that you can see here that it's a bit shiny. It's also possible to change the opacity, or the transparency of an object. There is also a way of displaying axes here, so you can see the coordinates of where you are in space. There's this orientation thing down below here can also be turned off and on like this. You can also do axis grid here. Then I also have, so these are the basic properties that we have on every kind of object you render. ParaView doesn't really have a file format that you use. So basically you load things into this and you can save everything as a state. So if I want to save this sphere here to something, I will go to the default state file format is PVSM. So that is a file that reads all the changes you made, also reads in the data you have specified and loads it into disk. You can save it either as a PVSM or actually as a Python state file. So if I do Python like this. Okay. If I go into documents, you can see here it's a Python file. So I will open it here. So you can see here that this is actually a Python file written in this PV Python format. So you can actually run this using the PV Python interpreter and recreate the visualization without having the user interface. So when you want to restart something, start from scratch, you do something called reset the session. That is an arrow here on the top here, which you press, and then it will empty the entire session. So it will empty the pipeline out, empty the window here like this. So how do you do visualizations in ParaView? So you have to load, first you have to have data sets. And you can do it in many ways. If you do open here, if we look at this drop-down box on supported files, you can see it supports a lot of data files that you can read into ParaView. So it's quite impressive in that sense. So I think most of the files you can find from most open source program, commercial codes, you can read directly into ParaView. I will do an example here that is provided with ParaView. So this is a cylinder with a heat source, and it has flow data from a flow simulation. So you can see here, I loaded it in. You can see here that it shows you some of the data fields that are connected to the nodes. So in ParaView, you can connect scalar values, vector values to nodes, to cells, that is kind of elements. Different ways. So you can see here, these dots here, that means that it's data connected to the nodes. And then you have data connected to surfaces as well, or elements in that case. So if you just press apply here, it loads the model into the ParaView section. You can see there's a hole there. You can see inside. So now you see it draws the cylinder here using the surface representation. And we want to color it by the temperature. So then we change from solid color here to the temperature field. Now you see it automatically changed to temperature visualization, added a color scale automatically here. So you see here I have a color scale here from blue to red. And if we go inside, you can see here that there's a heat source here in the middle of the cylinder that heats up the thing inside. I don't know what it is. So this is not very good visualization. It's just blue, and you have to look inside here. So how do we visualize the temperature distribution? And we have to cut up this model somewhere. So we will use something called a filter that will take the data and slice it. So in this case here, we have a clip filter, and we select the data we want to apply it to, click the filter. So now you see here that in the model, you've got this clipping plane here. You can move it here using the slider here. I don't do it now, but you can move it back and forth. In the properties here, I have X normal here, which is the one I have here. I can do Y normal, Z normal. You can also specify your own vector for the direction of the plane. And then you can press apply. Now you see it split the object in half, and it displays the section here, so you can see the temperatures inside. You can also see here what happens in the pipeline browser. So now there's an eye here that turns on and off the visibility of the object. So it automatically turned off the original visualization of the input data file. It added a clip filter here, and that eye is open here. If I click the eye, it disappears. If I click this eye, it will show both of them. You can also, there's a checkbox, is show plane. If you don't want to show that clipping plane, you can remove it like this. What I can do now is actually add the original visualization here, go down to opacity here, and make it transparent. So now you can see the outline of the object here as well. Another way of doing that is actually changing, instead of using opacity, we change it to wireframe. That is one way you can see also further to display wireframe. So set outline, and you get the outline of the entire model, which can be useful for visualizing as well. But I will keep it as a surface and I make it transparent like this. So if I want to change the colors here of the visualization, I go, in this case, I selected the original one here, the top, and then you can select here in coloring. You can press edit here, it will display the current color map used. You can also go and press the folder with a heart. It will display available color maps that you can use. So I'll just try to press the black border radiation here, press apply, close. Now you can see here that I have something that's more like a lead source visualization. You can also, if you want to change the view of the model, you can do here, you can reset the zoom. You can zoom to the data size. So if you have zoomed out here, you can press this one here to come back. You can also do zoom to a certain box like this. You want to see some details. You can zoom, set the axis view from different directions, from top, other side, different axes like this. So this model also contains vector data that is stored in the points of this visualization. If I turn on the so there are actually, you can see the grid, computational grid, and there are vector points stored on in each point here. So let's turn off here the surfaces, and we will do a streamline visualization. So we will kind of release particles that will create lines that follows the vector surface that is in the model. So there is a special view here called stream tracer. And now it's important, if you want to visualize all the entire model, you need to select the source that you want to apply the filter to. So if I apply the filter to the clip, it will only create streamlines within that clip. So only half the model. If I want to visualize all, I need to select the source here. Then I will create a separate branch of the browser that creates those visualizations. So then I do stream tracer. I go down. So here you can see here I have only one vector field, so you can only select that one. C type, I will release my points from a single source here. I will keep those ones. I will make the sphere a bit larger. So that it covers my model like this. So within the sphere, it will release streamlines. And I have 100 points that we will release. And I press apply. Now you can see here that I created streamlines here. And if I turn the model out, here you can see all the streamlines. I don't want to do that one. turn this one on, and then I make it a bit lower opacity. Now I can see all the streamlines in this movie. But they're a bit, they're just, now they are visualized using the same color scale as for the other one. So that is something we need to change. So we will color them by the vector field, like this. So now I have magnitude of V here. No, I do. Need to select the right object to modify. Here I change to vector. Now you see that the stream field is colored by the velocity of the stream. But I want the streamlines to look a bit more easy to see. So what I can do is I can add, create a three-dimensional tube for each of these streamlines. So I select the stream tracer. I create a filter here. And here you can see also all the filters you can apply to your data. So all of these are plugins that you can kind of plug together to create a visualization. So what I'm going to find here is it's hard to select this menu. But what I can do, instead of using this menu, you can do search. And you can type tube, and then it searches all the plugins for tube. And I will, many of the properties in ParaView also have this double arrows here, and that will actually look at the data and kind of create a reasonable value. So the radius of the tubes here is a bit large. So if I press here, you can see that they're a bit too big. So I can select there, and I can also resize the tubes a bit here. So now you can see the streamlines a little bit more three-dimensional. I can also do the specular highlighting here as well. Like that. So streamlines is one thing to visualize vector fields. You can also, if I turn this off here, I will select the data here. You can also create vectors in each of these points that visualize the vectors as well. So then you use a tool called glyph. Select the original data here, create glyph. Then you do, we will use V here. Select my magnitude. And then it will create vector arrows in the entire model at random and uniformly distributed in the volume. So here I say I want a maximum of 5,000 arrows. So here orientation already is the orientation of the arrow. So I give the vector field. I can also scale the arrows with the velocity component. And then if I just press apply here, it will draw three-dimensional arrows at each point where you have a vector. Sometimes these arrows can be hard to see. So you can also, instead of arrow here, you can select 2D glyph. That is the same thing as an arrow, but it's using lines. So if I do apply here, you can get these lines instead, these arrows instead that are without three dimensions, just a two-dimensional line oriented in space like this. So that was, I think we'll take a 10-minute break, and then I will do create the data for ParaView in Python. So let's continue. So I show you ParaView now, the application. So to be able to load data into ParaView, you need to specify your data in a certain file format. There is a default format in ParaView called VTK, which is a structure-full text-based file format, which supports these data structures I showed before: the image data, rectilinear grid, structured grid, unstructured points, polygonal data, and unstructured grid. So to use PyVTK, you need to install it. So in your Conda installation, you can do pip install PyVTK. So I will do this, and I will download a file that's with Perl 3, which we'll use later. So now I installed it. You use it. So now I'm using actually the wrong kind of import here, but from PyVTK import star, then I get all the classes that you can build data with. So the idea is that you create objects of certain classes to define the structures in the file. So in this case here, I create a polydata object, and the first parameter here is the points, so that you will use to connect your polygons to. So in this case here, I have points, and then I define the polygon topology here. I have 1, 2, 3, 4, 5, 6 polygons, and in this case, this will build up a cube. So I run this. Next, we want to, as this is a data visualization, you need to provide your data somehow to your visualization. So in this case, I want to attach scalar values to the points. So then I create the point data object containing my scalars, one for each of the points. So I 1, 2, 3, 4, 5, 6, 7, 8 points. And then I 1, 2, 3, 4, 5, 6, 7, 8. And I just give them values from 0 to 7. And here you can see also I can name the data. So if I put a name equals to sample scalars, that name will be visible in ParaView as well. So you can sort out the different data structures you have. Because you can have multiple point data to every point as well. So you can combine a lot of data into a single model. Point data is each point. Then you can have cell data. That is data that is connected to every element of your data. So in this case, we have polygonal data defined by triangles in this case. Not quads, sorry, quads. And then you can specify a data that is attached to the middle of the quad as well. So I have scalars here, and I have 6 sides. So I have 0, 1, 2, 3, 4, 5 attached to each of the sides. I call that field cell scalars. I add normals to the 3D model here. So that is to be able to do lighting and stuff like that, or cell normals. Then I can also do some other field data here. Not sure, I'm not sure it's required here, but scalar normals. You can also have, which I show later on, vector fields. So now I create cell data. And the final step, we need to create the data file. So then you create the VTK data object. This is this one here. And then you give it first a structure, basically the geometry of your data. You attach the point data and you attach the cell data to this file. Then you can create the file by specifying vtk.to file that will write the data to example1.vtk. And here the second parameter gives you if you want to write it in text file or as a binary file. If it's not too large, it's probably better to use the ASCII one. But if you have really large data, binary could be an option. So if I write this one here, run this one. I need to run things as well. Otherwise, this doesn't work. Like this. So and we can look at what we wrote here now. So in our file structure here now, you can see here that I have example1.btk, I have example1b.btk. And if I look into this one here, you can see here, this is the file format if I remove myself a bit. So it says here, a header here that identifies the version of the file. So this is a VTK data file version 2. Some extra text that is probably not needed. and then ASCII here, define that this is an ASCII-based file, and then it's called dataset polydata, and then it lists all the points, the polygons, cell data, and so on. So it's quite easy to read format here, but this class here will automatically take care of generating a correct file format. So if I now download this file, and it's a downloaded file, so I go back to ParaView here, open. You can see I have here example 1.vtk. I open this one here. You see here, the first thing, it doesn't show me anything. So let's just apply here. Now you can see here, it created a queue. And by default, it will select the sample scalars, which was attached to each point. And then it interpolates the color values from each point. So you can see here, I have values from 0 to 7. And because I added 1, 2, 3, 4, 5, 6, depending on the points. So there's a first point has 0 value, second point 1 value. That's why you get these different colors here. I can also change here to, you can see here the sample scalar, that is a point data. You can do the cell scalars here. Then you see here that every side here is a cell, because it's also it's not a volume data here, this is actually surface data. And every one of these here from 0 to 5. So each color of the size here is one of the values in the cell ID. So this is how you import it. If you look at surface with edges here, you can see here that's define actually a chord that you define with 4 sides will actually be 2 triangles when you export it like this. So for the next thing, I will reset again. So I have an empty session here. And then we go back again. So the next example here, we will do structured points. So in this case here, we have 3 by 4 by 6 grid points. And then we attach point data scalars to each of the grid points. And these are just valued here from, it has them starting from row 1, column, and so on. So here you can see that you have some values inside here. And these should be 3 by 4 by 6 numbers of values here. Then we run this. It should export something to example 2.vtk. So I will do download here. Go back to so now it by default just show the outline here. So I switch to surface with edges. So now you can see here, now we have a structured grid, 3, 1, 2, 3 by 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. And by default now it's colored solid. And you can, if I click here, you can see here I have scalar 0. I didn't give a name to the scalars. Then it names them automatically from 0 to 1 if it's scalar. And now you can see here that it seems to be correct. I have some values from 0 to 5 here, or 50 inside here, and that could be correct. So that was a structured grid. So what you also can do is, if you have an existing file name, and if you just want to update the values of an existing structure, you can actually load VTK data example 2, only structure, then it only loads this part here, structure, and then we provide the data here. So in this case, I have a function here of x, y, and z, and a computation here, and then I append structure scalar here, and I say f here, x, y, z, and it will compute the value by calling this function automatically. So let's run this. Let's see here, we have this one here. So this should be the same data structure as before. So if we do outline, we do circles with edges, same thing. But now the points have been calculated by the function instead. So let's see if it's there. You can see here I named the field x, y, z. So that came into ParaView. So now you can see here that it's a function that varies over the x, y, and z coordinates, which seems to be reasonable in this case. Reset again. Here's another example of a structured grid where you compute using a implicit for loop here. I don't think that's not so interesting. These are basically just examples of the same kind of data, just created in different ways. The final data structure in ParaView is the unstructured grid. In this case here, I have points, I have vectors at each point, and then I add the points here, and then I have the geometry defined by hexahedron, and then I specify the topology of the points, tetrahedrons, polygon, or topology of points again, polygon, triangle, strip, chord, triangle, line, vertex. And then I add a vector field to my data and a scalar field. So let's write this one here. So this is so here it's difficult to see here, but there's a line here, there's a chord, there's triangles, and different elements here. So as I said before, there is a point field with values here that varies the colors. Surface. So I can also visualize the vector field that I have here by using the glyphs here. And then I specify the vector fields here, scale using the vectors. So you can see here that the vectors here are also in this model here, attached to each point of the model. So you can have multiple data fields attached, multiple data to each point, multiple vectors to points, to the cells, and so on. So it's extremely flexible. So I'm now going to do a bit more complete example here. So in this case, we are going to use existing data that we have. It's actually from it's a vector field. And I will combine here what we learned from the NumPy lessons here as well. So we will import NumPy as MP, import PyVTK as VTK, and we will download this UVW data file. So the 16.2 megabyte file containing, we can see here that it contains variables x, y, z, so the position, and a vector for each position. There are 96 by 65 by 48 points. And then the data just comes below that. So the first thing we do is we load everything into a single field. We skip the first row because there are header information here, so we are not interested in that. To be able to export it used to ParaView, we have to divide it up into a points field and a vectors field. So we do some fancy array indexing here. So all the rows and the first 3 columns goes into points. All the rows and the 3 to the last one here goes into the vectors. The problem with ParaView today is that it doesn't accept NumPy arrays, it only accepts lists. But there's no big problem. We can do .toList that will convert the NumPy array to a list. So points is actually now a list, and vectors is also a nested list. So let's create our point data. We attach a vector field to each of the points and name it vec1. Then we create a structured grid. You remember the sizes of the fields here, 96, 65, 48. Attach our points to that, and we attach our points data to that as well. So points define the coordinates of the grid. This is the structure of the grid, and then for each point we attach the point data, which are vectors. Then we write it to a data file called UV. So let's see what we got. We got you see there is a uv.btk file. And we download that one. This is a bit larger file. We go back to ParaView. So usually when I first load something, just do a apply to just get the feel of the structure. So data seems to be formed like that. And we will do a surface here with edges. You can see the grid. So it seems to be more thinly oriented here at the surfaces. We can just color it with magnitude of the vectors. So here you can quickly see that the magnitude of the vector sizes. So let's see if we can visualize the vectors as well. So we will do streamline, vector 1, we do a point cloud, I'm sorry, a point cloud, and then where is the sphere? That. So you can see that there's a flow field going in one direction here. We can do 2. So you can see the flow field here as well inside this one. We can do close that one, and we do glyph here. Vector 1, to the width, scale by vector. So here you can see the vectors in the flow field. So now we went from a very pure text file to a vector visualization using the PyVTK tool. So let's do reset. The next example here, I will use a binary file actually. So this is a binary file, basically image file that contains elevation data from somewhere in Colorado. And also know that the 268 bytes, the beginning of this file is actually a header that we don't want to read. So the data is from the 268 position and forward. So we set the pointer at in the file using this FC command to jump over parts of the file. And we also know that we want to read it as binary. So RB means read binary. Then NumPy has a nice function called from file, which you can actually specify if we know the data structure, data type of each of the data stored in this file, which we know, which is unsigned bytes. We can tell NumPy to read into an array, and every value should be an unsigned byte. Next, we also know that the elevation data is 400 by 400. So we do a reshape here. Remember, reshape doesn't change the size. So there is already 400 by 400 elevation points in this file. So 400 by 400 just creates an array that is structured like we want to have it when we want to plot. We show the image here, and then we do create point data here, provide the scalars. We create a structured grid here using by 400 by 400 and attach the point data and create a file. So let's see here. That's a problem with notebooks in the cloud, that they don't have the files available. So you can see here the raw data file looks something like that. So there should be the Colorado River running here. So, and there is 160,000 unsigned bytes in this one, going from 0 to 255. So we should have elevation.vtk here, which we download. Go to ParaView. So it seems to be able to load this as an image. And by default, images are 2D objects. So I can't rotate it one. So we first have to switch view here to 3D. So now we have a flat surface like this. What we want to do now is we want to warp this by warp this surface with the data we have of the elevation. So now you can see it colors here by the scalar, but we can also do warp. Warp by scalar. And you can see here, select scalars here, which is a scalar field that we have. And we just put default and see what happens. So now you can see it's warped the image here by the actual values in the file. But you can see here that the surface is not very smooth. It's actually rather edgy. So what you can do as well, when you have done this warp, we can convert this mesh here to the surface mesh. So we do extract surface. There's no difference in this, but it creates a mesh that we can use to create, make it more smooth. And what we do in the next step here, I have to explain it here a bit. I don't know if you can see it here, but every surface here is visualized by a chord and probably a triangle, but the lighting is computed over the plane. And what you can do is you can create something, vertex normal that is interpolated at each corner of the triangle. And then that the graphics hardware interpolate and you get a more smooth model. And then you can apply another filter here called I didn't remember the name of it. Generate surface normals. That. And then we apply that. Now you can see here that it smoothed out the surface a bit. I think you also should make the scaling a bit like this. Now you can see here that it's more smooth surface. We can also see the plasticky like this. Of course, we should have a better color scale here as well. So we do. So this way you can do elevations, surfaces like this. So you can see here that the principle of ParaView is start with data, apply filters step by step to get data. That one will do in the exercise later. So in this example here, I will generate volume data. So you can see here that I generate smooth volume data, 128 by 128, and then in the size here, and this is parameters for the noise. And then I do create point data. I reshape it flat because I need to add it in a linear way here to a structured point grid by 128 by 128 by 128. So then we can see if we can visualize some volume data as well. And there should be something called ParaView. Decay. Set. Okay. It doesn't. It's still down though. This is a quite large data set compared to other ones, so that's why it takes some time. Should be done. seems to be a cube. That seems to be correct. I will look at the surface with edges here. So now I can see here it's a quite dense grid. If we do color it with scales here, so now I can see this is the Perlin noise I generated in the volume. And we can investigate here this in multiple ways. One option is to just look inside by using a split. And you can see inside. Perhaps not super useful. But we can also do three-dimensional contour lines using the contour tool here. Here you have to select the scalar you want to use. So by default, it just selects one data point here. So if we put 0 here, we can visualize the surface that has 0 value in this one. And then apply. So these are the surface that represents 0. A bit more speculation. We can also color it by. Yeah, of course, it has only one color because it's the 0 value. You can also do a range here, so we can do from. Let's see here. From here, it always fits in the min and 9 values. So we go 10. So we go from -1 to 1, 10 steps, generate. And then we do apply. Now you can see every surface here is one of the data points here. So that is one way of visualizing volume data. You can also do volume visualization. Then you switch to volume. Have to switch to this. This will show this. Here you can also change how the and create step function like this to kind of visualize certain points of the data. To look inside it as well. So this is a volume visualizer. You can then there is if you have a powerful enough, you can also do ray tracing on this to make it more much nicer with shadows and stuff like that. I think you can or different based volume rendering methods here. So that was volume rendering. That is actually what I have for today. I have put this video out later on. There is over one video. I will add a video on use case of ParaView as well, and you will get the work notebooks as well for this.